So this lesson is an introduction to the method of Lagrange multipliers, and I'm going to motivate it with the following question. Which point on the circle x squared plus y squared equals 4 yields the largest value for the function f of xy equals x plus 3y? So where do we think that will be? Now, to help us understand this, I'm going to go ahead and jump to a spreadsheet and do some analysis. Now, just to help you recognize, x squared plus y squared equals 4 is a circle, and the x values and also the y values can only range between -2 and 2. I'm going to look at a few of them, and I'm going to solve for y in my spreadsheet program. So y squared would be 4 minus x squared. Y would be plus or minus the square root of 4 minus x squared. But on my spreadsheet, I'm going to focus on the first quadrant. So x and y will be positive values and try to identify which is the maximum one that we see there. So I've got my x values. My y, I want to be the square root of 4 minus the x value squared. And of course, if x is 0, y would be 2, and we'll autofill this all the way down. And we are looking for a maximum value, right? I want the maximum value of x plus 3y, so equals the x value plus 3 times the y value. And what will that give me? That gives me that. Let's autofill this all the way down, and we're going to look for our maximum value. So what do we believe that largest value is going to be? So you can see at the very end we have 2. These numbers get bigger as we scroll up. So where do we see the largest value here in our list? And as we look for it, where are we going to get it? So we can see we're in the 6.32 area here. What's the largest one I see? 6.32455 seems to be the largest value I see. And that seems to occur when x is 0.63 approximately, and y is about 1.898. So just sort of keep that in mind. Again, there's our spreadsheet approximation that we'll keep in mind as now we're going to take a look at this geometrically. What do I mean by that? We're going to take a look at our circle, x squared plus y squared equals 4, in various lines. So x plus 3y equals various constants. You see, how do they relate to the circle? X squared plus y squared equals 4. So let's take a look. So there's the circle. And for example, if I ask x plus 3y equals -9, there are no points on the circle that allow for x plus 3y equals -9. If I ask x plus 3y equals 7, there are no points on the circle where x plus 3y equals 7. We are looking for values, right, that can actually land on the circle. So it's got to be somewhere in between. And I'm interested in the maximum value. So let's take a look at a few of these. These 2 points would give me x plus 3y equals 3. I can do better than that. Can I do x plus 3y equals 5? Sure, as again we saw from our spreadsheet, we think we can get as far as 6.32. So if I go to x plus 3y equals 6.32, how does that look? That looks almost tangent. You can see I have these 2 points here, somewhere between 0.56, an x of 0.56, and 0.70. So can we get even a little bit better from our spreadsheet? Let's take a look at what we had there. The spreadsheet gave us 6.32455. Does that look even better? So plugging in 6.32455, notice now it looks like a tangent at this level of amplification. But as we zoom in, we can see probably beyond the scope, but that's a pretty good approximation of a point of tangency. Now, what does the geometry tell us here? What am I looking for? I want you to recognize these lines, x plus 3y equals 3, x plus 3y equals 5, x plus 3y equals 6.32455. These are all level curves. So let's do an analysis of those level curves and build our procedure known as the method of Lagrange multipliers. X plus 3y equals c. They're a collection of level curves of that function f of xy equals x plus 3y. And we saw all of those lines going through that circle, these various level curves for different constants. Now, what about the circle itself? The circle itself was x squared plus y squared equals 4. Well, 4 is a constant, yes? So this is a level curve of what? Of the function g of xy. Equals x squared plus y squared. So we have a fixed level curve, which is a circle, and then we have a collection of level curves, which are lines. And what do we want to know about those? What do we want to say about them? The key idea is that the gradient is orthogonal to the level curves. So these green lines are level curves, and I'll go ahead and I'll draw one more in. And the gradient may be going this way, so that's orthogonal to the green level curve there. The black circle is also a level curve of g, and the gradient may be pointing that way because it's orthogonal. So we notice these two vectors are not pointing in the same direction. These two vectors are not pointing in the same direction, but at the point of tangency up here, notice, at the point of tangency, the gradient of the circle and the gradient of the line are pointing in the same direction. So the key idea to this model is, at the point of tangency, the gradients are parallel. So let's go back and take a look at our graph again and play with those circles and level curves to figure out where the points of tangency are going to be. So here are the two values of c that give us points of tangency. No surprise, x plus 3y is 6.32455. And there's our virtual point of intersection, 0.635 and 1.897. That will be our maximum value, yes? And our minimum value, kind of a mirror image, happened when c was negative 6.32455 down here. Again, as we're trying to find our point of intersection somewhere in that neighborhood. Doesn't seem to quite be hitting exactly there as well. So in each case, the gradients are orthogonal. Visualize the gradient here, orthogonal to the line and the circle. Visualize the gradient here, orthogonal to the line and the circle. So how do we do the algebra? The gradients are orthogonal, but they're pointing in the same direction, so that the gradient of f is parallel to the gradient of g. That does not mean the vectors are equal. That means one is a multiple of the other. So if gradient of f is parallel to the gradient of g, we say the gradient of f is some multiple, and it is traditional to use lambda, probably because of Lagrange, honoring his name. The gradient of f is some multiple of the gradient of g. So we need to find out what the gradient of f and the gradient of g are, and then do some algebra. So here are our two functions. F sub x is 1. F sub y is 3. So the gradient of f equals the vector 1, 3. On this side, g sub x is 2x. G sub y is 2y. So the gradient of g is 2x, comma, 2y. Our method of Lagrange multipliers is that the gradient of f is some multiple of the gradient of g. So we will say that 1, 3 is lambda times 2x, 2y. Our goal will be to solve for x, y, and lambda, but that seems tricky because we have 2 equations and 3 unknowns, but we will overcome that difficulty shortly. So looking at our vectors then, so we have 1, 3 multiplying in the lambda equals 2 lambda x, comma 2 lambda y. So one of my equations is 1 equals 2 lambda x. Another equation is 3 equals 2 lambda y. Well, what are we looking for? We're trying to find points x, y that are on the circle. So therefore, it's got to satisfy the equation of that circle, which was what? Which was x squared plus y squared equals 4. So these are the 3 equations we're going to try to solve to make sense out of this. Now, how do I do this? Typically, we're going to solve for lambda here. So 1 over 2x equals lambda, and 3 over 2y equals lambda. Well, if they both equal lambda, then they have to equal each other. Do we see how that's going to work? So if that's the case, 1 over 2x equals 3 over 2y. So we have this requirement as well as x squared plus y squared equals 4. So where do we go from there? So 2y equals 6x, which would tell me then that y equals 3x. And then we're going to go ahead and plug that in for y over here to find out what my x values are going to be. So we get x squared plus y squared, which will be 3x squared, equals 4. X squared plus 9x squared equals 4. 10x squared equals 4. X squared is 2/5, 4/10. So x is plus or minus the square root of 2/5. So continuing with this, then we've got to find the y value. Fine. So we have 2 possibilities for x. Recognize 1 is going to be a minimum and 1 is going to be a maximum. We have the square root of 2/5, which is what, I guess we can rationalize the denominator, make that a little simpler for us. Root 2 over root 5, multiply top and bottom by root 5. That gives us root 10 over 5. So I could have x is root 10 over 5 and negative root 10 over 5. That's the x value. So then the y value, which is 3 times x, would be 3 root 10 over 5 and negative 3 root 10 over 5. For kicks, let's see what those are as decimal approximation. Interestingly, we have 0.632, 1.897, negative 0.632, and I assume negative 1.8937 for the points on the circle that are optimal. For the points on the circle that are optimal. But then remember, my goal was to find the largest value of f of x, y equals x plus 3y. So here's our values. X root 10 over 5, y 3 root 10 over 5, x plus 3y 2 root 10. Similarly, negative root 10 over 5, negative 3 root 10 over 5, negative 2 root 10. So how does this compare to our geometry? So I put in the graph, root 10 over 5, 3 root 10 over 5, that's the red dot here. We see it, notice that as a point of tangency. Similarly, negative 10 root 5 and negative 3 root 10 over 5, that's the other point of tangency. 2 root 10, that's my maximum. Yes, that is my 6.32455 that we said before. Indeed, that is the maximum, and negative 6.32455 is the minimum.